Welcome to the Decent Crypto Podcast. Today is November 4th, and we are here to talk about Celestia. Matt, you're basically bouncing.
Celestia is a big topic. It's been like quite a bit of research actually going into this. Quite a bit of like opinions I had going in that I hold on to coming out. But we'll get to all of that in a minute. I think the big thing that kind of surprised me about doing the research for this one is it really calls into question like what is a blockchain doing, right? Like what are the different like pieces of a blockchain supposed to be like guaranteeing for you in exchange for like the fees that you're paying. So I think it'll be a really interesting episode because it's just so fundamentally like conceptual. And we usually talk about apps or individual rollups or smaller things. We don't really talk about like conceptually what is a blockchain. And today we're going to get into some of that, which should be pretty cool.
Yeah. So, let's start where we always start, the core fundamental question of the podcast. Why does this exist? So, Celestia, I guess we can start with Celestia itself, but Celestia is a data availability layer for rollups and for blockchain. So, like, what is data availability? What is the modular kind of blockchain stack that this represents? So, I guess we kind of need to define all of those terms, but like, why? Just broadly speaking, like, why does this even exist?
So I guess from the start, I would say about 50% of why does this exist, and this is pretty low for like a deep dive. About 50% of why this exists is scaling Ethereum, and then 50% other, right?
Mm-hmm.
So generally, I think if you think about blockchains, right, when you think about Celestia, you really have to start from the modular blockchain thesis, right? Because it's one module, right? It's one component of that. And
Mm-hmm.
interestingly, I think from a marketing perspective, when you think about modular blockchains, Celestia is the first name that comes to mind, even though it's just like one module of the modular stack, right?
Yeah.
And so they've really done a great job of defining, researching, owning this term. And when people think modular, they tend to think Celestia. So
Mm.
it's been a pretty interesting just like marketing approach, and I think they've done quite well with that. So the modular versus monolithic blockchain debate is a big one, right? Basically, on one hand, you have monolithic blockchains, things like Ethereum, and everything you need for Ethereum exists in the chain, right? It's got all
And
of
like,
the
what do you mean? What do you mean within the chain? Does that mean within like the software that you have to run if you are running a node or if you're a validator? Like within the chain, like does that mean within the transaction history? Like what exactly does that mean? Like if it's within the chain?
Yeah, so I guess the idea is if you're a validator, right, and you're running the validator software, you're taking part in everything that's required to run this chain. So I'll give you an example, right? Really, the way that I like to think about data availability is like if you think about a light client versus a full node, right? So a full node, it gets all of the block data. So you can kind of break the block down into like the block header and the block data. And the block data contains all the transactions, and the header contains like metadata. It contains this block's like, Merkle tree root hash, right? It's got the previous block's hash, right? And it's got like some metadata around timestamp and whatever, right? Um, but as a light client, you're just ingesting those. You're getting what is the current block number, and what is the like canonical block hash of the latest block. So this is a way to sort of like follow along with the chain's consensus. As it adds a new block, you get the latest block header, and then you kind of know what page everyone's on, right? If you're like reading through a book together or whatever. So uh, the problem with that is if you just have the block header and you just have the previous block's header, and you don't have the transactions, it's actually not possible for you to verify from that whether like the current block is a valid state, right? So imagine I try to send a transaction and I have 10 ETH and I'm trying to send you like 50 ETH, right? You could make a block header that represents that transaction happening, that represents like the update of balances, where I send you 50, my balance goes down by 10 and your balance goes up by 50. That's not like a valid transaction, but you could construct a block header that would reflect that transaction happening, right?
Okay.
And so as a light client, you're putting a lot of trust in, right? You don't see the transactions happening, and if something goes like wrong, or if someone's trying to like break the rules and submit an invalid transaction, there's no way for you to know that without actually having the block data, without having the transaction
Right.
timestamps.
Okay.
Um, so it's really, it comes down to this notion of like a light client versus like a full node, right? In Ethereum, basically everyone is running a full node. If they're participating in the consensus of the system, if they're participating in the like data availability, et cetera, there's all these different responsibilities within the system. And with Ethereum, it's like one or two pieces of software that are like very heavily intertangled that run all this stuff. And the modular or the monolithic blockchain approach is basically like you're less flexible, right? So you could imagine wanting to have a blockchain that uses the same stake as Ethereum and the same consensus as Ethereum, but has like a completely different virtual machine or something, right? You can't do that. You can't like break that out. The system is like you get what you get, right? It is one and done. It's like it's non-negotiable. The modular blockchain thesis says, look, devs might want to be able to like break down what they're working on, right? So some people might want to innovate on the virtual machine. Some people might want it. So Solana, for example, the SVM is like pretty wild and creative. You have parallel transaction execution. You have like all sorts of interesting things, right? You might want to
Yeah.
innovate, or you might want a private virtual machine, right? Something like Aztec or whatever, where like privacy is like baked into the VM itself, or secret network, right? Um, or you might want to have like a different kind of consensus, right? Maybe you want proof of work, right?
Mm.
And you want to like innovate on that, or proof of space time or whatever, right? There's all these different components that you can innovate on, but as a dev, you might not want to like worry about all the other components here. Maybe you think you just have the best virtual machine and you want to make that available for other people to use for like a licensing fee or something, right? Um, well, with Ethereum, it's like the VM, the consensus, the data availability, the security, it all sort of comes together, right? And in Solana, similarly, the SVM is like, it's not, you can't break it out from Solana consensus, from the Solana staking token, from proof of history, from all this other stuff, right? Um,
Yeah.
and so it kind of hinders innovation, is like one approach. The other way of looking at it is it could hinder efficiency, right? So the SVM is clearly much more efficient at processing transactions than Ethereum, right? Um, but it does so at the cost of decentralization, right? It's much more expensive to run a full node that actually is keeping track of all the transactions and knows the state of the chain. And also the, like little shit, like the block export doesn't work very well, right? Because it's super expensive to process all of this data. Maybe you
Mm.
could break down these concerns, right? And you could separate them into like people being able to innovate just on the efficient virtual machine, which has much higher throughput, without sacrificing decentralization or consensus or whatever from Ethereum. And that's sort of the vision behind the modular blockchain thesis, is it gives you more customizability.
Okay.
Um,
And so, did Ethereum kind of lay out this modular blockchain thesis from its inception? Like, I know this kind of comes more from the Cosmos world initially, but was this always the vision for Ethereum? Or has it kind of evolved, or has it kind of like found itself or stumbled into this vision because of all of its scaling issues and because of kind of not completely redesigning the whole chain, or like not, wanting to redesign the whole chain. And so kind of looking at this different approach, kind of using roll ups and using like basically breaking out all of these different components that we have of the blockchain into essentially like different, not exactly chains themselves, but like different kind of services.
So it's a good question. And I think this is kind of what I mean by it's like 50-50, right? So it's like, yeah, Celestia was kind of born out of a project called Lazy Ledger.
Mm-hmm.
which originated within the Cosmos community, right? And it's been kind of built hand in hand with a lot of people that have roles, in the Ethereum world, researching rollups and all of that. But it didn't really come into the Ethereum picture until rollups became kind of like this the scaling vision. Um, Celestia itself can be useful for scaling all sorts of things, right? Scaling Bitcoin, for example. So one of the examples for like breaking out data availability in particular is like I can have bigger Bitcoin blocks than I could otherwise have because I put all the transaction data over here and I don't worry about like, when it comes to consensus, I'm just passing along the block headers. But when it comes to the data availability, I can use a service like Celestia that's like specialized in that. Same thing for
Mm.
Ethereum. Like the roll up vision of the world is very much like that, right? So I guess maybe it would be helpful. Maybe we take a step back. Let's break down like what are the different roles in the modular blockchain stack.
Yeah,
Um,
yeah.
this has always been something that I've found to not be well explained, and I'm
Yeah, not
gonna
at all. Like essentially, like even I think this is kind of even more fundamental than like the different parts of the modular blockchain stack. Like this is almost like what does a blockchain even do, right? Like you're basically kind of breaking down like what are the different pieces of like yeah, what is now the modular blockchain stack that need to be performed for all of our transaction stacks we go through and for us to be able to interact the way we do on chain. There are various kind of components of it that yeah, like you said many times you don't even think about. So yeah, can you just run through them real quick and then we'll go into each one.
yeah. So effectively, there's like four kind of like components, right? There's execution, settlement, consensus, and data availability.
Mm-hmm.
And the reason that these things don't generally get explained well is because they're not super like comparable. If you're thinking of each of them as like one equal sized component of everything, I would say that's like not the right way to conceptualize it. By far, the biggest part of this is execution,
Yeah.
and then consensus and data availability. And like the settlement part of it is almost just like a little extra feature, right? So I think this is one reason
Mm-hmm.
that people don't tend to explain it well is settlement is like an afterthought, really. So um, let's think about execution. So imagine you are like let's just think about like a typical blockchain like program, right? That's running on a computer. It does a
Mm-hmm.
couple of things. It has to communicate with all the other nodes to reach like a consensus state, and then it has to take the transactions that are coming in and one by one apply them to its vision of the world. So let's start with like a very simple, like if you think about just very simple blockchain, right? Maybe it has balances and it has a balance for you and a balance for me, right? And we're
Yeah.
counting, I don't know, like we're counting the number of beers we've had, right?
Yeah. Okay.
um so
And
so
like real quick, let's pause. So when you say like let's take this blockchain. It says that, I have this balance, you have this balance. You're essentially like in the real world, you're almost like kind of saying like this validator that's keeping track of this ledger. Every single validator that is running this chain is essentially doing this exact same thing
yes.
on their own and broadcasting what they're doing to every other validator that is running this chain as well, or at least kind of the end result. They're not going to broadcast every portion of it, but they're going to broadcast the end result. Um,
Yeah. So if you
so
think about like a new block, it's getting propagated to everyone else, right? And
yeah,
then in Cosmos, everybody's got to sign, like to sign off, like, hey, I recognize this block as the next block, right? And then that gets passed
hmm
around to everyone else. So yeah, it's like, this is like the very essence of blockchains, right? Is having multiple computers in like a decentralized like way coordinate on the
hmm
state of a thing, right? And
hmm
so one of those things can be a ledger, right, where it counts
hmm
things, right, or moves balances back and forth. But it could easily just be like a chessboard, right, where
yeah,
you
yeah,
have the state of the chessboard, and that is like the state of the machine. And so
hmm
in computer science terms, you would call this a state machine because it's a machine
hmm
that has a state, and then it has like things that you can like state transitions that you can apply to it. that
Yeah.
change the state of the machine. For
And
example,
yeah, and like a
transaction.
state transition, yeah, is as simple as like moving one chess piece forward or making a transaction or literally anything that has changed the system, um, or any of the
Mhm.
components in the system. That is basically just a state transition.
Yeah,
Um,
and generally we would use the word state transition and transaction to mean the same thing, right? Generally
yeah.
speaking. So if you go through like the Cosmos docs, they're interchangeable, right?
Hmm.
So we have our super simple blockchain, and all it's doing is counting how many beers we're drinking. Shout out
Hmm.
Karan. Karan drinks beer again now, which is pretty cool
Yeah.
after a long
Wild.
hiatus.
What times we live in?
um, so, okay, so let's say you submit a transaction, you say, I'm signing that I have drank one beer, right? And like, forget the Oracle problem. You drink a beer, you sign the thing,
Yeah.
and it updates your
Hmm.
count by one. So
Hmm.
if you think about the state of this machine, it can actually be really, really small, right? It can be like
Hmm.
a zero and a zero to start. It'd be two zeros, right?
Yeah.
And
Yeah.
then you drink one, and your zero goes to one, right?
Yeah.
And then I drink one, and that zero goes to one. And so it's like each of these just like
Hmm.
a single byte or a single bit
Yeah.
changing in the state machine, right?
Right.
And if you think of Ethereum, like side note, if you read like the docs, like what is Ethereum? It's an infinite size state machine. So as the number of things grows, like the state machine itself just grows infinitely, right? And so like your address has some part of the state that is like held for it, and then it can just iteratively get bigger and bigger as you accrue more state to your address. So
Mm.
we might start out with 2 bits to represent the system, 0 beers for me, 0 beers for you, and then it could expand to 4 bits or 8 bits or whatever,
Yeah.
right?
Right. Right.
So anyway, we have the state, and then a transaction gets submitted to the network of decentralized like validators that are applying the state transition, right? So the
Hmm.
state transition comes in a block, right? Whoever's like the leader sees the state transition, see this transaction, and they're like, okay, I'm gonna apply this change to the state, right? And this is the new block. Everybody look at your states, make sure that you're updating them to reflect that this transaction is happening, right? Um, and so the validators all in parallel are doing this. They're taking the state and then they're applying some transition to it to represent the new state. That's what the execution client does. That's the execution part. So it's taking the transactions
Okay.
themselves and applying them to the state machine according to the rules of the system, right? So maybe you can only drink 1 beer at a time. So if you try to submit a transaction that you're drinking 2 beers, that one will get rejected, right? And you only apply transitions from valid transactions, right? Um,
Okay. Yeah. Yeah. Makes sense.
so the execution part of the modular stack is that all it does is it keeps track of the state and it updates it to reflect transitions.
Okay. Got it.
That's the
That's
core of
it.
it. Then you have
Gotcha.
the consensus. So in Ethereum, that's the execution client, is what you would call it. In Cosmos, you would call it, I want to say, like the application, right?
Okay.
Um, and then you have the consensus module of it, right?
Hmm.
In Ethereum, this is the consensus layer, I think is what we call it, execution layer, consensus layer.
Hmm.
In Cosmos,
And
this is
like,
Tendermint, right? Hmm?
yeah, and in a real world sense, like as a validator, can you like in Ethereum, can you choose to only run the execution portion and not run the consensus portion, or is it basically just kind of you're running the same piece of software and these are just parts of it that it kind of I don't know it does, or how exactly does it work?
Yeah. So if you think of it like yeah, so someone that's running like a node that's not like a staker, that's just keeping track of the state of the chain,
Yeah.
they would be doing that exactly. They would be running
Okay,
just the
got it.
execution client, right?
Yeah. Okay, so that's basically just what a full node is.
Yeah,
Like not a
uh,
validator,
yeah,
just a full node.
yeah, exactly. So they're not proposing blocks. They're not making decisions on the state of the machine, or the sorry, the the state of the chain, right?
Yeah.
Or which which canonical chain you're on or whatever, right? all of that stuff happens in the consensus client, right? And
Yeah.
so the consensus client, it handles things like leader selection. So who's going to be the person proposing, or which machine is going to propose the block, right? It handles propagating that to everyone. It handles voting on like, okay, I've seen the next block and I am attesting that I've seen it and that this is the next block, right? It handles like the mechanisms of block proposal and propagation. That's like the consensus client, right? It's the part that makes sure
Okay.
that consensus is reached for every incremental block. And then you could think
Okay.
of it a little bit like you're in class, right? Someone goes up to the front of the board and they're like, hey, Karan drank one beer, right? And all of the
Hmm.
students are sitting here like with their little notepads writing Karan one beer, right?
Hmm.
That's sort of like the execution layers, like, version of it, right?
Mm. Okay.
Um,
Got it. So like, yeah, to basically play this analogy out so far, like the execution was basically us saying like, look, updating or basically, broadcasting out like, look, we've updated our state, or whatever. Basically, we've each drinking, one beer. And there are, let's say, people watching or just around in the bar that see all this happen. They all basically update the state of the whole network, right? They say, you drink one beer, I drink one beer. One person actually gets selected to kind of write that to the chain. Like how exactly, like let's go through like how consensus actually works. Um, like how in this situation, like how does it actually work? Like if everybody kind of agrees, like okay, or like if everybody's seeing essentially the same thing, right? Like everybody's seeing transactions come through, everybody's essentially creating the same kind of block header, right? Um, like how what happens next?
okay. So transactions are sitting in the mempool, right? Because we
Yeah,
got a lot of friends and we're all drinking beers, right?
yeah, yeah.
And someone is the leader, right? So they're like, and that's like the technical term, right? They're the
Yeah.
validator that's going to propose the block. They're the block proposer for this next block number two, let's call it, right?
Hmm.
uh, they look at the mempool and they're like, okay, I have this list of transactions, and here's I'm going to order them in terms of like gas price or tips or whatever, right? If it's Bitcoin, right? I'm going to take them, apply them, simulate applying them to the state of the machine to make sure that like each of them represents like a valid state transition that's like signed by the person who sent it, or like, is not like double spending or whatever, right? I'm going to make sure that like this set of transactions represents a set of valid state transitions. And then I apply that to my state machine and I'm like, okay, this is the new state of the machine. So from that, I can compute like the Merkle tree root that represents the state of the machine. Think of it as like a hash of the state machine, right? I'm going to take that. That goes into my block header. I'm going to take the current date and time. That goes into my block header. And then the transactions that I applied, I put those in the block data, right? And I take all of that and I say to the network, hey, everyone, this is the next block, right? And then if I have a light client, okay, so like forgetting light client, all the validators are now looking at each other like, okay, you agree, you're good, okay, we get everybody to sign off, and then that becomes like finalized as the next block, right? In tender minutes, 66% of the validators sign off, and it becomes finalized, right? Um, so uh, so then everybody looks and they say, okay, this is the next block. Let me just quickly update my state machine, because the next person who comes in is going to have to know what the valid state machine, what the current state of the chain is, right? So let's say you spend one Bitcoin and you only had one. Well, I need to update my state machine to the state of my machine to reflect that you spent it, so that when I go in to make the next block, I know what valid transactions are, like which ones will succeed and which ones will fail,
Yeah.
right? Um, so that part, like the simulation of like the actual execution of stuff, like the transaction data could just be whatever, right? It could be words, it could be
Yeah,
empty,
yeah.
it could be anything, right? And the consensus client will not give a shit, right? It's just about forming consensus on data, right? But the blockchain like business logic, the rules of engagement, the way that the virtual machine works, the maximum number of beers you can drink per transaction, all of that stuff happens in the application part of this, right? That's the
Mm,
execution. That's the execution part, right?
right. Okay.
Um,
But like, if there is a transaction that's, well, let's say it's not valid or it's a double spend or whatever, that gets rejected at the consensus layer. Is that right?
it's so that part I think gets handled in like the in Cosmos you would call it the ABCI, like the application blockchain something integration. I think it's basically the part where they talk to each other. That's where it'll get
Okay, got it.
rejected, right?
Yeah.
But most blockchains, when you get an incoming transaction in your mempool, will try to simulate it a little bit anyway. And if the signature is invalid or something, they just reject it out of hand at that point,
Mm,
and you never try to
yeah, yeah.
simulate applying it to the state machine, right?
Okay, got it.
Just for like spam prevention.
Yeah.
So
And you
that's
can
kind
kind
of
of see that. You can kind of see that too, like where in the chain your or like in the chain of events, not in like the actual blockchain, like your transaction is failing based on whether or not you're ending up paying gas, even if it's a failed transaction, or how much gas you are paying, because sometimes it'll actually process part of the transaction, but then it'll fail because whatever you didn't set the tip
the
high enough,
minimum high
or
enough or whatever.
yeah,
Yeah.
yeah, exactly, yeah. So generally, yeah, like you said, if it's something like you don't have enough balance, like it you just won't even accept that transaction.
Yes.
But if it's something like, yeah, like you don't have enough ETH for gas to pay for, or not that, like let's say you just didn't set the gas high enough to get your transaction, high enough in the mempool, then it's a consensus kind of issue.
Yeah.
Um,
That's the idea. So consensus
okay,
is just like coming to a consensus in a decentralized manner on data, right? It's
yeah,
decentralized consensus of just data agreement. And then
hmm,
whatever that data does is like kind of not consensus, not the consensus layer's concern, right? It's the
okay,
concern of the application layer, the execution environment. That's the component that's really handling this stuff,
that
right?
makes sense, yeah. But
So
generally, it is the same like validator set that is kind of executing transactions and coming to and kind of handling the consensus layer generally.
yeah,
But it doesn't have to be.
So
Is that kind of the idea?
In Ethereum, you run two clients. You run, and this is new since proof of stake. So you run the consensus client and you run the execution client. And
Okay.
each of those is a separate piece of software that's running on the same computer, and they have like a designated channel to communicate with each other. But each of them is its own separate piece of software.
Okay, that makes sense. And like, is this basically at this point they're just running on kind of these like NVIDIA GPUs that are like, I don't know, kind of custom tweaked a little bit to
Well,
um
thanks to proof of stake, everything can run on like a super tiny little client, right? Like you could have like a shitty
okay, so
$20
you
Raspberry Pi running both of these things.
yeah. And it doesn't even and it doesn't actually matter like how fast the hardware is, or how like potent it is or anything like that.
I mean, with Solana, you have to, right? Because the sheer
Yeah.
number of updates to the state machine coming through at any given point in time is very, very high. And so that's where like your hardware bottleneck comes in, right? But with Ethereum, there's actually very few state transitions coming at your execution layer. And so you really don't need much firepower in order to like keep track of it, right?
Mm,
So this is what people say about like Ethereum and proof of stake and it being like more decentralization friendly is that like you have just like very, very lightweight applications that are running, right? And I think most Cosmos blockchains are similar, right? Like
mm,
you can have relatively high throughput with like commodity hardware and like never worry about it. The reason ETH used to use
okay.
GPUs was for the mining, right?
Yeah. Right. Okay. I still figured that there was like some basic level of hardware requirement because it's still processing like I don't know how many transactions a second, but it's still like I don't know, it's a couple hundred or whatever, right?
I mean, in ETH, I think it's like
And
15.
okay.
It's pretty slow. Yeah.
Um, yeah, it's quite slow.
Yeah.
Okay.
Um,
Interesting.
so,
Um,
So anyway,
Okay, so then the
those are the
next,
first two
yes, and then
components. So there's execution and consensus, right?
yeah.
Then we have this question of data availability, right? And
Well, should we just cover settlement real quick since you said it's kind of like a just an
well, I
add-on?
think the way that I would think about settlement is like bridging. It's really mostly about bridging, right? And if you're like if you're running a layer two, I guess we'll jump ahead a little bit. If you're running a layer two and you need to get some assets off of the ETH L1 and into your chain, and then someone wants to claim them back on the L1, that's like what the settlement really means here, right?
Mm,
Is like being able to access assets on the other chain. I would mostly use that as like what is settlement anyway, right? Um, you could say there's other things, but they are related to consensus. So like with the ZK rollups, like proof verification happens, and that's part of like settlement, right? Um, I guess, yeah. In a lightweight sense, settlement is about being able to like bridge safely, right? Or like reaching finality that a bigger system includes. Um, Whether that gives you access to assets or whether that gives you like just finality on the state of the chain itself, right? That's like those can all be part of it. But the settlement part of it is kind of intertwined with consensus. But if you're going to use consensus to mean we agree on the state of the chain in a way that carries some form of finality, then the only incremental thing that settlement gets you is bridging, really. That's how I conceptualize it. But you can already kind of see if settlement involves finality, which some people would say it does, then it has a lot to do with consensus, right? Because consensus also has a lot to do with finality. Um, like if you're going to have any meaningful amount of consensus, it has to be consensus toward something that's not going to change, right? Um,
yeah.
so it's a
Hmm.
little it's a little weird, right? But it's not like for and this is why it's kind of like a side note one is like most of what settlement is supposed to be doing is really referring to finality, and I would argue that's kind of just part of consensus.
Hmm.
But we'll walk through an example in a minute with layer two that'll make
Yeah.
this all feel just like way cleaner.
Hmm.
And the last component here is data availability. And there's a sort of like macro question here of like why does data availability exist, right? Like what does it
Yeah.
mean, right?
Right.
Um, and this is where we get back to like full node light client, right? So data availability it's like if you're okay, not everybody can operate a full node, right? It's just like it's too much to ask of people. It's a lot of responsibility. It's like hardware costs, like just the storage of the whole chain and all of the data for a full archival node is pretty big for Ethereum these days, right?
Yeah. Like
Um,
it gets to a few hundred gigs in terms of memory alone, right? Like to store all the transactions.
I think, well, there's memory and storage, right? For memory, I think you can still run Ethereum with like 8 gigs of memory, I mean, for most clients, but there's like, I think it's on the order of terabytes, like one or two,
Oh, it's into the terabytes. Oh, okay.
for just like all of the transaction history of the chain,
Yeah,
right?
yeah. Hmm.
So if you can't really expect everyone out there to be running a full node, but you want more decentralization than just a few people running these things in server farms somewhere. So you introduce this notion of like the light client, right? And a light client does a couple of things, but the main thing that it does is it just keeps track of like what is the current like header of the chain, right? Like what is the current block header for the current latest block. And using that, you can do some interesting things like check balances or whatever, right? But it doesn't like as we said before, the block headers don't guarantee that the correct state transitions are being applied properly. So somebody could be like, hey, I have a transaction and this should be rejected by the network, right? That prints me 10 ETH out of nowhere, right? I'm just going to mint myself 10 ETH, right? um, well, the block header, you can make a block header that reflects that invalid state of the chain. So we have the state of the chain before block header n minus one, right? And then you apply this invalid state transition. Let's say this is just one transaction in this block, right? Just to make it really simple. You apply that, you come up with the next header that is like header n, right? To a light client, that's going to look like a valid header, but it doesn't represent a valid state transition, right? The transaction that was applied should not have been able to get through the execution layer, right? And now that we're sort of breaking these things apart, like we have to kind of worry now about like, are people keeping track of whether the transactions that are being applied are valid or not, right? So an invalid transaction is like Matt gets 10 ETH for free, right?
Hmm.
It can still you can still produce like a valid block header on like based on that if nobody's checking or if nobody knows what the transactions are. And so you need to have some way for people to come in and prove that there was fraud committed there, that there was a fraudulent transaction, that there was a non an invalid transaction, like an invalid state transition applied to the state of the machine, if that makes sense. So Matt's balance goes up by 10 magically is an invalid state transition. Um, well, if everyone's just running a light client, nobody knows what the transactions are, right? In the limit case, or like, maybe there's a cartel that they're the only ones listening to all the transactions, right? If everyone's just running a light client and we're like, oh yeah, this is the state of the chain, you could check Matt's balance and it might reflect 10, right? And we don't want that because that was totally invalid. So the way that the trust model kind of works is light clients are always they're always trusting full nodes to come in and say, whoa, 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 that block's invalid. I'm not reaching consensus on that block, right? This is not the
Hmm.
next block. And that's really how it should be, is like the block gets sort of like, the block proposer says, this is the next block, and it's got this like invalid transaction in it. Everybody else
Hmm.
takes that block, they try to apply it to their state machine, they're like, this doesn't work, right? And they're like, I can't move the needle forward to this state of the world because Matt has an invalid 10 ETH balance.
Yeah. Right.
I'm not going to propagate this. I'm not going to sign off on it. This is not cool. This is not the next block. The state of the world is still whatever the last block was because this block is invalid. Um, the light clients are always sort of implicitly trusting the full nodes to be doing that, to be checking to make sure that the state transitions that are being applied are valid. And in order to like check that the state transitions that are being applied are valid, the full nodes, they need to know what the transactions are, right? Like that's the only there's no error on that, right? Like someone needs to know what
Yeah.
the transactions are that are being proposed in the block, right? Light clients don't necessarily need that, but full nodes do. Um, and this is where we start to touch like optimistic rollups, right? So with an optimistic rollup, the way it works is every like update to the state machine is written down to Ethereum with as call data with all of the transaction
Yeah.
data that happened on the state machine, right? And this is pretty
Yeah. Yeah.
expensive. Like Arbitrum, I think we were looking at the numbers earlier, pays $175,000 in fees to Ethereum just to like be a place where the data gets announced, right? So the
Yeah.
whole idea is the data needs to be like anybody that cares to needs to be able to know what the transactions were.
Yeah. And so essentially what this means is that what Arbitrum is doing is taking Arbitrum transaction data that is happening on the L2 and writing it to the Ethereum L1 as call data. And like, can you explain what exactly call data is?
Yeah. So call data is data that like is circulated as part of the transaction, right? But not written to the chain. So this is actually pretty straightforward. So you and I each drink one beer, right? Someone then comes in, where back to our old example. I drink one more beer, but I want to leave a little note on the fridge, like, "Hey, man, sorry, I drank all the beers." Right? I can apply a little note to my transaction that says, "Hey, by the way, I drank the last beer. I'm not going to drink anymore tonight," or something, or "Hey, I'm driving," or whatever. Right? Any note that you want to append to the end of the transaction, I can just add that, right? As a variable, basically. So when we talk about call data, it's because you have a function that you're calling with this as like an input to the function. And it might not do anything, like it doesn't change the state of the machine. The state of the machine is still very much my beer count goes up by one. That's it, right? I drank a beer. But anybody that's listening for all of the transactions that are happening, and anybody that's running a full node or whatever, they see the transactions, they see what arguments they're getting called with, they see the inputs, those functions, they see the function calls, they see all the transaction data, including the call data. And so it becomes a place for people to be able to listen for data, right? It's like a bulletin board almost, right? Where it's like, this doesn't change the state of the Ethereum like machine, right? It doesn't change the state machine. I'm never actually writing that stuff to the chain. The chain is still very much just like my number of beers, your number of beers. But anybody that's keeping like all of the list of transactions that have been applied to the machine, they have to keep all the data associated with them to make sure they're being executed properly, including this one, including my little note that says I drank the last beer. Um, so it would be very, very expensive to like people might say, okay, well, Matt, this is an infinite machine and you're gonna drink 10 beers or 100 beers or whatever. It's not always just gonna be like 2 bits, 0 and 0, 0 and 1, 1 and 1, whatever. Like stuff's gonna expand. Why not just write your note to the chain? And the answer is that that's very expensive. And in Ethereum, it's a little cheaper to just write stuff as call data versus writing it directly to the chain.
And so, like, okay, I'm still kind of not sure if you're not writing it to the chain, how are other people able to view it in the future? Or, like, why is it even useful, right? Like, if it's
Um,
not written on chain, like, what exactly, like, is it still able to be indexed in some way where you can still kind of take it and read it off chain, like in a browser window or something like that? Or, like, what is the exact use if
yeah.
it's not actually on chain?
So I think yeah, it's being like the data is being propagated in the same way that all the chain updates are being propagated, right? But the reason that this is slightly worse than just writing it on chain is if I have like a smart contract or something that needs to reference a part of the
Oh,
state machine, it can't read it,
mm,
right? Like it's not
okay, got it.
accessible to the state of the chain. And so like clients that just need to access the state of the chain, they're not going to know about this data. But you're effectively using the Ethereum network and the gossiping protocol and all of that as a place to just like broadcast data, right?
Got it. It's like if the bar just put a bulletin board and anybody could just like start tacking stuff on. And it's like,
Yeah,
look, we'll still make you pay, but it's just gonna be way cheaper to do that than buy a beer, you know?
exactly.
Okay.
But then it also doesn't show up, for example, when the bar goes to settle up tabs or do accounting or whatever. Like it doesn't count. Like
Yeah,
the
yeah. Or like
bartender
on the
doesn't know anything about
menu.
it. Yeah,
Yeah, yeah.
exactly.
Okay. Got it, got
Um,
it.
so
This is
that's what
great.
call
We
data
have a whole
is.
analogy.
And this is probably the worst, the worst version of modular blockchain explanation ever. um,
um,
so, so look, why is this important, right? So the back to optimistic rollups and check out our L2's deep dive if you haven't. But like Arbitrum or Optimism or whoever, they have a whole bunch of transactions, right? And they're getting posted to the L1 as call data. So everybody that's listening to Ethereum can, and the reason that using Ethereum is a good idea is like, if you care about Ethereum, then you're listening to Ethereum in some way, right? Or you know someone
mhm,
that's listening to Ethereum or whatever. With Optimism, it's linked to Ethereum. So, you know, you might as well just post all your data to Ethereum too, because like people are bridging in and out from Ethereum. So anybody that gives a shit about Optimism, they also give a shit about Ethereum. And so using just the Ethereum blockchain and all the data associated with it, at any point in time, you can reconstruct what happened on Optimism, right? And
mhm,
so Ethereum is the only thing you need basically to make sure that you're keeping up with the state of optimism. So every new like optimism block or mega block or whatever takes all the transactions that have been done on optimism, broadcasts them to everybody in the Ethereum world, right? And it's as call data and it says, look, these are the transactions, these are the state transitions that are being applied. And some of them include state transitions that are requesting withdrawals of assets. So some people are trying to bridge off of optimism and back to the L1. They're trying to get some of that ETH that's like sitting in the deposit contract. In Arbitrum, they call it like an inbox or an outbox, right?
mhm.
and they're trying to like send it to themselves on the L1. So this is where fraud proofs come in. So basically, imagine like remember my example before that magically mints me 10 ETH, right? Um, I try to like if let's say I'm in cahoots with Optimism, right? The people that are posting this data, and I'm like, yo guys, I got a great idea. Let's mint me 10 ETH. Let's just take 10 of the ETH that's like supposed to belong to someone else and just like give it to my address on the L1, right? What do you say? And they're like, yeah, yeah, sure, let's give it a shot, right? Like you'll split it with us, right? And I'm like, yeah, yeah, sure.
Hmm.
um,
Yeah.
so so that transaction's like not valid, right? It's an invalid state transition. If you try to follow the rules of the execution layer, you won't be allowed to do it.
Right.
But you could try, right? And so
Of
I'm
which execution layer? Of the Optimism execution layer or the Ethereum execution layer?
uh both, right? So it would be like it shouldn't be valid in the optimism execution layer, and as a result, it shouldn't correspondingly allow me to pull out 10 ETH
Right,
when
right.
on the L1, right?
Yeah.
So with a ZK rollup, it's like way more straightforward. Any transaction that happens, you generate a proof that that's a valid
Yeah.
transaction, right? Easy
Yeah, yeah.
peasy, and
And it
then you
just
submit
gets
it
verified right there.
right there
Right?
on the
And
L1
then
every single time.
yeah.
Yeah.
Right.
Um, with optimistic rollups, it's a little bit harder, right? Because some you want to make it so that any full remember this idea that like clients are trusting full nodes to come in and like make sure that they're holding the block producers accountable, right? So full nodes, they're keeping track of all the transactions. The light clients are not, right? Similarly here, everybody's sort of trusting that like someone's double checking that the transactions on optimism are valid, right? That we're not just like magically minting Matt 10 ETH and then that's going to let him take it out on the L1. So this is where we have a 7-day waiting period. And the idea is anybody should be able to look at the list of transactions, see that mine is invalid, and be like, guys, what the fuck? This is an invalid transaction. I'm not applying this update to the state of optimism. So the state of optimism right now, the proposal is like, look, we have 500 transactions, including the one where Matt magically gets 10 ETH. And we think we should update the state of optimism's chain from A to B, where B is like a state where I have 10 more ETH than I should, right? And you need to have a way for someone to come in and be like, whoa, 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 whoa. Here's proof that Matt's trying to commit fraud here, right? That that's not a valid state transition. That this set of 500 transactions is invalid, and we're rejecting that as the next block, right? And so ignore all of this and try again without the fraud, please, right? Um, so in order for that to happen, people need to be able to see that I'm trying to get this invalid transaction through. And that's what data availability is for. It's for the broadcasting of transaction data so that people can come in and double check that the state transitions that are being applied are valid. That's really the
Okay, I
crux of
see.
it, right? Um,
Okay.
so it's most useful for optimistic rollups, I would say. That's like by far
Mm.
the strongest use case today. Um,
And this whole kind of concept of data availability, is this basically just a different way of providing the solution that is currently in place with using Ethereum call data?
Yeah, that's the idea. So the Ethereum call data is a form of data availability, right? But it's pretty expensive. So there's a proposal called EIP 4844, which will create. We have writing directly to the chain, super expensive, right? We have writing with call data, cheaper, right? Because it doesn't actually update the state of Ethereum, but it's still going through the same pipes, right? Then we have one called blobs, right? And this creates a third EIP484 creates a third type of way to post data to the Ethereum like network, right? Blob storage, and it's expected to be about 10% the cost of writing call data, right? So if Arbitrum is spending 175K roughly per day for their call data expenses, This will take it down to about 17.5K. Pretty meaningful, right? Um, but in exchange for that, what you get is the data is not permanent, right? So it's going to get what's called pruned, just like a plant, right? You prune out like the data that you no longer need. And we're thinking it's going to be about, everyone seems to be thinking it's going to be about 30 days. And so in that 30 days, like the data is guaranteed to be available. That's thus data availability. Like you're guaranteed to be able to download it from somewhere if you care, to double check that the optimism or arbitrum chain is not getting like invalid state transitions applied to it, right?
Hmm.
And that's
Okay,
where
so I
the
have one question on that. So you mentioned for these optimistic rollups that there's like a 7 day window where people can basically contest the validity of certain transactions. Um, how exactly does that work if there is a valid claim that there is you know um, like a state transition that shouldn't have happened, let's say, right? So like let's say like 4 days have gone by or something like that, and there is somebody basically posts a fraud proof, uh, for a state transition that happened like 4 days prior. Like what happens to the state of the chain at that point?
um okay, so the state of the chain, like officially, like in terms of like settlement and finality, there's a with rollups there's a couple of places that it happens. So if I send a transaction on Optimism to like buy one NFT or something, it's sort of kind of final immediately because I write it, there's a centralized sequencer, and if I trust them, then I know that that's not going to get forked out, right? um, but it's not really final until 7 days have gone by. And so this could potentially wreak havoc, is basically the idea. Nothing is really final until 7 days have gone by, and so the final state of the chain is always 7 days ago. And what would happen if there was fraud committed and there was a proof? I think it would roll back, which would suck.
Yeah,
Like, because
that
it's a
would break
headache,
a
right?
ton of things because
And
so
yeah,
much. Yeah, at that point, like maybe people have even. Yeah, like who knows what people have done and what
well, I'll
transactions
give
have
you
taken
one.
place. Like
I'll give you one example of something bad that would break is like, what if someone took funds off of Optimism? Like Coinbase
exactly.
supports direct ETH deposit and withdrawal from Optimism.
Yeah, yeah.
That's they're trusting, right? They're trusting someone to do that. Maybe it's Synapse, maybe it's someone else, right? That's really bad because if like that could open up the door for like all sorts of double spend problems, right? Say it gets say I withdraw my ETH to Coinbase, I sell it for USDC, I'm happy, and then the chain gets rolled back and now I have my ETH again. That's really bad. um, and so in practice, it would be extremely problematic. But that's also why we have centralized sequencers. I
Yeah,
don't think a fraud proof
exactly.
has ever been submitted. Well, Optimism, first of all, doesn't have fraud proofs. Like there is no way to do that. Arbitrum has
So I was
fraud
gonna
proofs
say, I think you mean in theory that would be
in
really
theory.
bad. In
I mean,
practice,
they have.
that would just never happen because there is no way for it to ever happen.
Dude, yeah. I mean, it's amazing. Like you read the Celestia docs, and like one of the things they harp on is just like social consensus is big. They're like, we believe social consensus is like the biggest thing. But if you have that, then like here's all the like theoretical shit, right? Social consensus is everything, right? So so anyway, you have your 7 day period, it gets submitted, whatever, right? But just in case, we'll keep the data around for like 30 days is the idea. Um,
Okay. And
and
that's like
the
what Celestia does, or that's
that's all still using Ethereum. That's EIP 4844 blob space,
oh,
right?
got it, got it, got it, got it. Yeah, yeah.
Luckily for us, Celestia is pretty similar to that. So Celestia finally getting to it, right? So we have this need for data availability where it's like we have to post the transactions somewhere, and it needs to be like verifiable that like people can actually access that data, right? Because if you're going to have fraud proofs, You need to be able to prove them. And in order to do that, you need to have the transaction data somewhere. Like it needs to be possible to download the data and double check it yourself, right? That's what data availability is all about, right? It's about if I needed to, could I download it, right? At least for the period of time that I care about it, right?
So is
Um,
that just data availability? Does that essentially just mean like short term, temporary kind of like data storage?
yeah, I would almost call it data downloadability, right?
Okay. Yeah,
It's
yeah.
downloadable for now, right? It's downloadable temporarily. Yeah, exactly. So and the reason that like using Ethereum is an attractive option, getting back to it because I don't know if I worded it super well before. If you're on Optimism, right, and you're posting a fraud proof for Optimism, you're posting it to Ethereum anyway. And so it's very convenient to just have to listen to Ethereum. That's it. You don't have to run like two clients or whatever, right? Listening to another chain where the transactions are going. If you're going to eventually submit your fraud proof to Ethereum, you might as well just use Ethereum, right? The idea is like that way, people who care can just listen to Ethereum and like they don't have to worry about the rest of the world, right? Um, but Celestia offers a slightly different model. So with Celestia, the idea is you can specialize, right? It's modular. Why not modularize it into like its own standalone service just for data availability? So what you'll have is you'll have stakers that are securing the network by coming to a consensus on the state. And the state in Celestia is data. So it's like block data gets added as a blob, right? So you have like 10 transactions from Optimism, let's say. They're a blob of just like zeros and ones that gets posted to the chain, and you pay gas. You pay gas per byte that's getting written, right? It's like a fee market. It's just like an L1, pretty much standard. Except that you will, so by paying that, you get a guarantee in exchange for your fee. You get a guarantee that like the validator set will keep that data up and available to download for at least 30 days, right? Um, Sorry, I think I lost your audio. Can you hear me?
Okay, yeah.
Oh yeah.
So I muted myself for some reason. So it's essentially the exact same as what like blobs are going to be on like with 4844.
Yeah, that's the idea. And currently pruning isn't even enabled on Celestia yet, so it is like permanent-ish, right? But that's the idea is you post your blob and then Celestia handles that part for you. Um, so this begs the question of like what are you getting, right? Like okay, you're getting the guarantee that the decentralized network will keep your data up and available. How do you check? Well, you can use something called a data availability proof, right? And this is I would say that proof here is not a good word for it. It's like too strong of a word. But imagine okay, so the technique that they use is something called data availability sampling, right? Where you basically ask the Celestia nodes for one chunk of the data that you care about. So say you care about block number 10 of Matt and Karan's like beer drinking adventure chain, right? Um, and block number 10 has like 30 transactions in it. You say, look, I want 10% of the transaction data, please. And you can have a light client, right, that just gets that 10%. And you say, I would like 10% more, please. And then your light client gets 10% at a time. Eventually, probabilistically, because the way it works is you ask for random like portions of it. Probabilistically,
Okay.
you can get to a point pretty quickly where there's like a 99% chance that all of the block is there. Um,
Yeah, by just sampling like a couple random like small little portions of the data.
Yeah, so this is something that I know we're like running long on this episode, but I think this is actually really cool to talk about. This is using something called erasure coding, right? And erasure coding is really interesting. It's a data like replication technique. So computers are not like infallible. Like CPUs have little noises in them, DVDs get little scratches on them, and so actually when it comes to like data storage, you tend to have a fair amount of duplication of data. And you want to like make sure that you can restore the original data from like some copy of it or some like sharded copy of it. So I'll give you a really easy example. Let's say I want to send you three numbers, right? 1, 3, and 5. Let's say that, right? Well, maybe our network is a little bit noisy. And so if I send you three numbers, there's a reasonable chance that like one of them just gets dropped, right, from the list, right? What I can do is I can include a checksum that adds 1, 3, and 5. So 1 plus 3 is 4 plus 5 is 9, right? Uh,
Yeah.
and I'll send you four numbers instead. So I'm going to send you 1, 3, 5, 9. So let's say one of these numbers gets dropped. You can always know for sure that you can recreate the original three, right? So from one blank 5, 9, you can always regenerate the three from 1, 5, blank 9, right? You can, et cetera, right? Like, so,
Yeah,
so you
yeah,
kind of get
yeah.
the idea. This is like the most simple, and this is what you'd call like ideal, like erasure coding, right? Where it's like fully replicable, right? Like you can always get the data again from the original inputs, but you're adding metadata or you're making multiple copies or something to make sure that you can always generate the original data. Generally, this uses like really large numbers and multiplication and polynomials and like other like more interesting transformations of the original data rather than just like summing it, right? But like uh and for for block space, the way this kind of looks is each Celestia node is storing multiple transformations of each transaction, right? And by querying for like a set, you can verify that like the checksum is good, or you can verify that like even if you're missing that blank set of data, like you can always recreate it from the transformed version of it that you're getting. So it's like erasure coding is this technique that basically, and this sounds really strange, it's the opposite kind of compression, where you have one set of data, you have lots and lots of different transformations of it, and based on sort of like randomly querying those, you can get pretty good confidence that you could generate the original data if you need to, right?
Interesting.
Yeah, it's
That's
interpolation.
pretty cool.
Yeah,
Huh.
it's fucking wild.
Wow.
And so this is where the
Yeah.
Celestia version of the world comes into play, where the vision is something like you have all these little tiny light clients. Where I have one on my phone, I have one on my computer, I have one in my AirPods, right? One on my Kindle, and each of them is sort of sampling a little bit randomly for any of the chains that it cares about, just to double check that the data is actually there, right? That it's actually available for download. None of them actually needs to download the whole chain. So you avoid this issue that we have with like Solana, where you need a big ass beefy computer to download the whole chain and all the transactions. But each of
Yeah.
them sort of individually can come to this conclusion that the data is there, right? And then anybody that cares to, if they see something that they think might be a fraudulent state transition, they can download the data and prove it. Um,
Hmm.
and that's where data availability sampling comes in, and how I think if you asked people at Celestia, they would say they see this as a much more robust approach to decentralization, because the every piece of the assumptions here is like, if I need to download that data, like if there's fraud, and if I need to download the data, or if someone needs to download the data, right? Like, could they possibly have access to it if they needed to? And with data availability sampling, you can say, yeah, there's a 99.5% chance that like that's possible, right? And so this is all very like unhappy path, right? In a happy path, in a happy world, it's like there's no fraud, done deal, right? So this is all
Yeah.
just like, just in case there's fraud, and just in case you need to prove it, and just in case like I don't have a copy of it with me, could I download those transactions, right? Um,
Interesting. Yeah, yeah, yeah. That's still wild. Like I still am trying to understand fully how you could piece the data together. I'm probably
Dude, I went pretty
not
deep on
the exact.
Wikipedia. It's hard.
Yeah. Yeah, I was gonna say I'm probably not the exact demo for the people who understand this kind of stuff, but it's super cool. Um, so for the idea here is like you basically have this kind of open canvas for data availability. All the roll ups can essentially just start basically writing their data to this space. Like I don't know what you call it. Do you call it a chain? Do you call it like a data availability layer, or like
Yeah, you call
what
it a data
exactly?
availability layer. Exactly.
Yeah. Um, so yeah, people like the idea here is essentially all roll ups or any roll ups can use this. Right. And
Yeah.
then yeah, okay. Um, interesting. Okay.
Yeah.
And is it it is live now? Right.
Yeah.
Like are
So
roll ups using it? Like what's the standard still at this point?
So it's really early. So they went live in testnet a while ago. They went live in mainnet much more recently. They airdropped the
Mm-hmm.
token to a bunch of builders. So the token is TIA, TIA.
Mm-hmm.
And the way they ran this airdrop was like super interesting. They basically went through a bunch of like GitHub repos for open source like crypto like code bases or crypto related code bases. And they said, look, if you have had a minimum number n commits to any of these repos, you can claim the Celestia airdrop. Um, and it was beefy. I mean, there are people out there that made like 20 grand off of it, right? It's like a really decent sized airdrop. You had to go in and verify your GitHub account and make some commit that like had your address that you wanted to claim it on. But they airdropped the token and mainnet is up and running. And the interesting thing about Celestia is as a business, how do they get their product into the hands of their consumers, right? So the roll-up developers, right? And for a lot of roll-up aligned products, the way to do that is through roll-up as a service providers, RASs, right? So Celestia's got one, or they have like an SDK called RollKit, I think, which is used by a bunch of the RAS providers. Um, but it looks a lot like Web 2, where you're like, I need to be like the de facto software standard that this like roll up as a service provider integrates, right? Or I need to be like on their menu. And so that's kind of like their go to market strategy. I think it's very early days, right? Celestia's main competitors here are one, Ethereum, and especially after EIP 4844. Two,
Yeah, yeah.
um, to EigenDA, which is eigenlayers like data availability. Because think about what you're doing. Like you're staking some token and you're saying, I have a copy of this data for at least 30 days. And then if anybody hits you up with it, you can give it back. And if you don't have that data, you get slashed, is basically the idea. Right.
Right, right.
So you could do that with eigenlayer as well. You can stake your liquid staked ETH and provide
Yeah.
this as like a service, right? Um,
Mm.
so it's Ethereum,
That's a pretty good model
EigenDA.
for Eigenlayer, actually. Huh.
Yeah, and Eigenlayer, they're gonna do shit like like a much more diverse set of stuff, right? So it's gonna be data availability. There'll probably be bridges that are like staked through Eigenlayer, right? Where you put up some tokens as like a stake that like I saw a bridge transaction and it's not fraudulent. Like let the tokens through, and if someone can prove you wrong, then you get sloshed. Oracles potentially, right? Like anything for staking, Eigenlayer is going to attempt, right? It's not just like other chains; it's also like services like this. Um, so yeah, and then there's Polygon had one which was called Polygon Avail. Now it's just called Avail, and the models are very similar, right? And the roll-up
Yeah,
as a service providers are very similar,
yeah,
and
yeah.
I'm not sold that this needs to exist.
Right,
um,
right.
that any of this needs to exist, right? So
Yeah. So, what is your long term kind of take here? What exactly do you think is the future of kind of this whole world of roll up as a service, data availability, a lot of these kind of companies that look pretty similar to Web2 SaaS models? Like, how are you kind of seeing this space? I mean, we both were pretty interested, or we're I don't know. We were talking afterwards about our last episode with Patrick Bush, where he basically was super intrigued by Solana after thinking about data availability. So, like, what are your general thoughts? How do you think about the future of Celestia and like this whole kind of space?
So there's one thing that I find kind of interesting about Celestia, and that's this idea of like a sovereign rollup, where you're not using, say, Ethereum as settlement, and in order to get assets in and out, you have to figure out your own bridge or whatever. So you would split the world into smart contract rollups. All of the ones that we have today are those. They have deposit and withdrawal addresses, like contracts on Ethereum that handle the bridging of assets to and from the L1. It's contract rollups, right? You also have sovereign rollups, and those are a little bit trippier. So if you think about, like, let's say your chain never touches Ethereum, like, and all we have is just like a chain, right? Like it's counting beers or something, right? Um, all we need to do is have like some computer that's sitting there as a sequencer taking in the transactions, telling Celestia about them, and Celestia handles consensus and ordering and data availability and all this other shit, right? Consensus is not necessarily permanent, but it's permanent enough. And then how do you interpret the data? Because Celestia is ultimately doing the same thing as the Ethereum consensus client. It's just coming to a consensus on data, right? And making sure that it's available, right? So it doesn't know anything about our rollup. It doesn't know anything about how to parse a transaction that says Matt drank a beer, right? It's just ones and zeros to Celestia, right? It's just charging per byte stored and that's it, right? Um, so how would you like parse that? How do you interpret that? Well, you can have what you would call like a headless rollup, right? Where you and I are running maybe just like one piece of software, which is just the application. And all it does is it reads transactions from Celestia, applies them as, state transitions, and just keeps a copy of the chain. And that's all it does. It doesn't do any consensus. It doesn't even really
Hmm.
handle like transaction propagation or anything. All it's doing is like listening for transactions on Celestia and applying them. And it's like this
Yeah.
wild thing of like all it's doing is the interpretation of the data. That's the headless rollup vision of the world, which I think like that's the most extreme version of this, right? Where it's like all you need is you can use Celestia, right? You can use Celestia for consensus, you can use it for data availability, and then as a result, it's transaction ordering and all that. What happens on Celestia counts. And then how does it work? Well, for that, you apply the execution layer and it tosses invalid transactions or whatever. But from the like stream of transaction data, it can just like create the state of the chain on its own. Um,
Yeah.
I don't know how it's useful, but it's kind of trippy, right? Um, a headless rollup.
uh, yeah. Huh. Interesting. These
Okay.
names are just really bad, though, for sure.
Yeah.
We need to do something about the names.
Well, they kind of need to be useful. So, okay, now that we've talked about this for over an hour, I'm so freaking bearish. Like, I just
mm,
can't even, right? Like,
yeah.
I just can't even.
Yeah. No. Like I'm becoming more of a Solana bull day by day.
Yeah, me too.
Yeah. It's like, damn. Wait, hold on. This kind of a lot of this is just like you said, VC circle jerk.
Yeah.
Um.
So why does the modular blockchain
Yeah.
thesis appeal to VCs? This is like we'll run it back. Here's my thesis, right? It appeals to VCs
Yeah.
because it gives them more pieces of the system to invest in. So if you like
Yeah.
Ethereum, you can only buy ETH. If you like the modular blockchain thesis, you can buy Optimism and Arbitrum and Celestia and God knows what
Yeah.
else, Eigen token, right? Like
Yeah.
it gives you more investable tokens, and sort of
Right.
like the unspoken rule is like from last cycle is like if you get in tokens early you will make money from them when they go liquid. That's
Yeah.
sort of like everyone's
Yeah.
kind of in consensus there, right? And so having more at bats, having more opportunities is like very good for VCs, right? Being able to invest in each part of the stack separately, it's more tokens. And to a degree, the token is the product. That's how crypto works, right? That's part of what's beautiful about it. But it does create like over engineering of shit like this, right? And I'm I'm not sold that it makes sense. I'm really not. I think look, like we already have way too much block space, right? Like we have way more than we know what to do with, and it's posting to Ethereum and it's making money, yeah, but that's about to get 10x cheaper, right? What happens then? How much cheaper does Celestia have to be relative to Ethereum, right? Because the
Yeah,
advantage of
yeah.
being on Ethereum is everybody's just like there, right?
Mm-hmm.
It's like having a Twitter space and all your friends are there, and you just have to listen to that one spaces, and you know that you're getting complete information. Having to listen to Ethereum for deposit withdrawals of assets, having to listen in addition to Celestia for transaction data, having to do the data availability sampling, it's just like a way heavier lift for what? For more block space? Like we already have too much. Um,
Yeah.
and the I think did you read the Kyle Samani like in defense of like or his like modular versus monolithic like piece on I think it was on his Substack or something like a
No,
few
I
months ago.
haven't.
This was a great piece. He's basically
Mm-hmm.
he goes in, he makes the argument. He's like, look, show me the innovation. Show me which part
Mm-hmm.
of this has actually enabled innovative like changes to each of these layers that genuinely created a better product for people, right?
Mm.
And he's like, I kind of can't, right? There's not much. Like the splitting of execution and consensus and data availability and all of this, like nobody's really doing that much better at it than the monolithic chains. And nobody does that better than Solana. And obviously he's like pumping his bags, right? But I think he's got a really good point, which is that like this whole thing is A, to scale Ethereum or whatever. Well, we already have too much block space. B, to enable the customizability of each of these different layers. And each of these different layers is like not really doing much other than having its own token.
Hmm. I am also equally bearish. I am becoming more of a Solana bull day by day. I yeah, I don't know. Like I just like okay, let's just close out with the token. Do you see value in the token? Like obviously we both said we're bearish, but like what is the token actually for? Like is there any value there?
Uh, this is a tough one. This is a tough one, right? Basically, I'm bearish on the token on the basis of Ethereum is making it cheaper to just do it on the L1. Like, and I'm also bearish Ethereum Ether for that reason. Like, I think it's like a pretty
Mm-hmm.
strong bear case for Ether is that like if we're moving toward this L2 vision of the world, like, and we're making it cheaper for L2s to post their transaction data, like, what the fuck are we doing, right? Like you lose like a lot of revenue, right? Um, what is it even for, right? If it's just going to be like super cheap to post this stuff, like what is Ethereum for? um but that does create a lot of pressure, I think, from the cost perspective for Celestia. And I think it has less economic security than Ethereum, right? And it's as a result it's got to be like way cheaper. um
Mm.
and so I'm bearish on the token for that reason. I don't think revenues are going to be there. And I think that the value prop is too confusing for the average person. I mean, I barely understand it, right? And it's just not something that is memeable, you know? Like it's not
Yeah.
quite gigabrained enough to like be bullish on like like a professor coin, right? Like it doesn't feel like a professor coin, right? It
No.
doesn't feel like a right curve play. It doesn't feel like a left curve play. That's Solana, obviously.
Mm-hmm.
And it feels pretty mid curve to me. It's like trying to innovate on stuff that doesn't need innovation, or I don't know. Like it's building things that are possible. Yeah, the problem with Celestia is that the things that it makes possible have basically zero product market fit.
Mm. Interesting.
Yeah, that's my bear case.
Mm. Well, this whole episode has been a bear case. All right. Well, I think that was pretty good. You got anything else?
No. I think look, we'll have someone from Celestia on, and they can tell us why we're completely wrong or something.
Yeah,
I don't
they can give
know.
us the bull case. Yeah. All right. Well, yeah, this is great. Yeah, this is the Celestia deep dive. We'll be back in a few days to do our next recap. It's been a bit since we did our last recap. So yeah, have a great week, everybody, and until next time, stay decent.